Yeah, welcome everybody. Not a huge audience today, but this is maybe a little bit of an esoteric topic with the Boost library. I'm not, great expert. I, in fact, started to use C++ back, I think, almost right after Strostrup himself introduced it. So I've kind of been working away, but I like to keep up on whatever I can. And the MPI stuff, of course, really important for or critical for parallel programming on the new systems. I'm just going to do a quick introduction. There's nothing really sort of earth-shaking in the Boost approach to things, the Boost MPI library. It's more that it fixes up a lot of the little things, and for me particularly, it cuts down on a lot of the bug fixing really well. So I'm pretty impressed with it, and have sort of started to move a lot of some of my bigger codes just to use it, just because it cleans things up so nicely. So I'm going to go through pretty quickly. Just got a couple of examples at the end, and then I'll ask questions whenever. I'll see if I can answer them. Won't pretend I'm a great expert, but we'll just keep going. So I thought I'd start a little bit with old-fashioned C++ and where it's going and what's happening. I think recently, last sort of 10 years, C++ has really changed. The working groups, I've got the names up there, the ISO and the IEC technical committees got involved and have set up a number of new standards. And in particular, that C++ 11 version, 2011 version, was, in my view, great. A lot of good stuff, multi-threading, generic programming, performance updates, requirements, auto, lambda functions. There was a lot added to C++ 11. C++ 14 was essentially bug fixes and extras, and I haven't really started to have a look at C++ 17 yet. I think, according to the GNU guys, it's supported by the GNU compilers. Rather, maybe worryingly, they say they're starting to remove the deprecated features, but actually, look at some of the details. Those are good ideas. And of course, C++ 20 is in progress. I'm looking forward to that. So just a quick overview there, and let me remind you a little bit about the old original C++, Bjarne Strostrup, that C++ programming language text. I think that's a great text still. It's well worthwhile having a quick read. It's pretty straightforward, and it talks about why he did what he did, and I really like that. It gets you a good idea. I put down some of these notes that Strostrup wanted to make the language really, really flexible so that you could choose your own style. Back then, of course, the in thing was the object-oriented approach, but it's continued to do that, continue to add different ways of approaching your development and to encourage programmers to use whatever they feel like. A key from Strostrup was that anything should be useful. He wasn't too interested in while he was a computer scientist, he wasn't too interested in the sort of theory of programming. And then that third bullet point, I think that's what caused a lot of has caused tons of issues with C++, that useful features are more important than protecting against misuse. A lot of the more modern languages are in fact there to protect you. The scripting language approach, they do a lot for you, in particular with memory management and such, while languages like C and C++ are pretty low level and ask you to do a lot yourself. And if you really want to shoot yourself in the foot, you can indeed do so. And then the final point, performance is important. There wasn't supposed to be anything between C++ and assembly. It's a compiled language. And the fact that there are features in the language, but you as a programmer don't use them, should not impact performance at all. So I think you can see why C++, therefore, is actually a pretty good language for high-performance computing. Certainly Fortran is right there as well, came way, way before C++, but I think has some similar aims and philosophies around the approach. So C++ does well in our kind of environment. Now let me mention templates a bit, because of course, the Boost library is a template library. Templates were, as far as I remember, they were actually introduced by Stroustrup way back. And my first introduction to them was writing finite element codes, where one wanted to define an element template and then use that template when you had different elements coming in. You could do a lot of stuff with that, and it's not easy. I remember working on some of that and trying to get all those templates right, but once you did get them right, it was great. So a template, a compile time polymorphism. So you know, the compiler actually uses the template to write code. I think that's for us a really important point, that that we are not assuming that the library has already compiled and optimized and done whatever it needs to do. However you run your compiler with whatever optimizations you want are applied to the templates as well. And in fact, all modern compilers are tuned to minimize abstraction penalties for those templates. The standard template library was the first library of those kind of things like data structures, you know, iterators, vectors, arrays, those kinds of things were all in that. So that was the standard, the STL. That's pretty much been superseded or included in now the C++ standard library. It's just all called the standard library, and whenever they can do it, they use a template. A template's just far more efficient. So again, I think this is really kind of nice for our HPC environment. There are some issues, of course, with templates. The compiler generates sometimes a lot of code from all these templates that it's got handy, and indeed, when you start including the Boost libraries, compile time, even on a big fast machine, can start to increase pretty drastically. It's less of a problem with these fast machines, but it's still there. Yeah, I kind of live with it at the moment. Error messages, well, you know, all the way along, C++ error messages have been a bit of a pain. And with templates, where you may have templates creating templates, the tree of error messages generated by one rather minor error can be pages and pages. So that is a pain, and it's one that I don't know if it'll ever be solved, but it'd be really nice. I find searching back through a whole error dump for sometimes just a missing angle bracket. Yeah, it's a pain. But yeah, we got to at the moment we're living with that kind of thing. Those are syntax errors. Once you've actually got it compiling, usually the runtime errors are a lot easier. At least I find them so. Another one, just maybe a minor one at the bottom. We got all these iterators so that you can iterate through data structures, do the for loops, all that kind of thing. But those sometimes have overheads. It's kind of easy sometimes when you're sorting through some kind of queue or whatever to end up really slow if there's a poor choice of iterators. And again, maybe that just emphasizes that C++ fact that generally C++ isn't too worried about yourself shooting you in the foot. It allows you to do an awful lot of things. So the C++ standard library is now pretty big. There's a lot of stuff there, and you have to be kind of aware of what's going on there. And hopefully, you know, when you learn C++, you learn nowadays quite a bit of the details. Now, there were a bunch of old C++ MPI bindings. MPI 1 included C++ bindings. And I gave an example there. It's pretty much a straight one-to-one with classic C MPI. You know, you always had MPI underscore receive or MPI underscore init. Well, the MPI bindings just had a namespace MPI and put the functions in that namespace. Turned out that almost no one used those. There were a few bugs that pretty rapidly came in. I think, as you might remember, MPI was originally a Fortran operation and it was kind of ported over to C. And the forum guys back then, I think didn't really have enough C++ expertise, so it was a good start, but it wasn't great. And I say they were one-to-one, so there was really no advantage. And in fact, MPI 3 came along, and no one felt like continuing those old C++ MPI bindings. And in particular, Boost had already started up their own MPI template library, and Boost uses the old ones. So as of the latest, I think C++ 17 and the MPI 3, you won't get all those old bindings. So there was a good start there, and you may get, and it's relatively easy to get mixed up there sometimes when you see some old examples. But these are the new things. So let me dive right in and just give a short example, just to give you some idea of what the Boost library gives you. There's, of course, these are templates, and templates are, of course, in the header files. So right away, up at the top, there's an include, and you're going to include the Boost MPI libraries. Everything in Boost looks like Boost / something, and there are now, I think, hundreds of Boost libraries. So going to the Boost pages, I've got some links later, and having a look there for whatever looks good is handy. I usually just give myself a namespace. Oops. Just to mean that I don't have to type Boost : every time and explicitly have the namespace. And then here's a sort of classic little MPI example where I'm sending some data, in this case an integer, from one processor to another one. And in MPI, you start off, Boost MPI, start off with an environment, get the world, and that's the communicator. So remember, the communicator is the set of processors that you've got access to. The usual rank, but now we've got a type world, an object, and .rank will give us the processor ID. So you know, every MPI program needs to know which rank it's on. Of course, I'm going to tag the data, and well, I put master equals 0 just for clarity. So if the rank equals master, then there's a world.receive, receive from any source with messages that are tagged. I usually put some tag in, and put the received message, in this case an integer, into that integer I. And then the send is just a similar send, world.send master tag rank. So this sends from me, or sorry, it says from the local processor to the master, tags it, and the actual integer it sends was just the rank. Nothing spam. Maybe I shouldn't have used that, but it just sends an integer. So you can get the idea there. Pretty straightforward, and pretty much one-to-one with classic MPI at this level. And then compiling and linking, you can just use the MPI scripts. They work fine, MPI CC and MPI run. You need a flag. The GNU compiler does not, I think it uses as default C++ 98. So if you wanted to use later C++'s -std equal C++ 11, 14 works fine there. Haven't tried 17. Yeah, you then run the MPI C++ compiler, and the little extra that, at least on my Linux box, is that I have to get the linker flags both before and after the compile step. You know, in the old days, you used to have to do this because of the looped referrals, where one referral might in the linker might refer to something and then back again. So you had to make sure you had the whole thing organized. I'm a little surprised at this, but it seems to come up quite regularly. I don't know if anybody else has had any experience with that, or have tried to link Boost libraries. And of course, one thing here that does show up is that the Boost operation attempts to make everything it can a template for performance reasons, but here and there they have to actually write some standard libraries, so you do have to link some libraries. And the library standard, you'll see it, I've got Boost _ MPI. Yeah, so that's the one related to and include with Boost /MPI.hpp. The serialization library, I'll talk about that shortly, but that one almost always is needed so that Boost knows how to serialize data and send it back and forth. Anyhow, and then MPI run works fine with however number of processors you need, and if you're one of our big systems, of course, you'll be submitting this through a batch script. So I thought I'd put this example up. Everybody who's done MPI has seen it. This is just send a string from one processor to another one. So there's a sender and receiver process, and the sender up top there is just going to send this string. And what it has to do, sending a string, is to figure out the length of the string, figure out how many bytes there are in it, send that as an integer, and then send the string itself. And the receiver has to do just the opposite. It has to receive the size of whatever it's getting. It has to allocate memory to store the incoming message, and then it has to receive that message into that memory space. And it has to be kind of careful to make sure that it deletes and does the memory management, all that kind of thing. So Classic MPI is really pretty low level here. It doesn't understand much about C++. It knows what integers, characters, floats, reals are, and you have to handle the format of how you send and receive that stuff. This is the part that has, I think, at least in my career, driven me nuts. It's trivial stuff. You just have to make sure your message goes. But I spend a huge amount of time for anything like a complex object or class, trying to get all the formats of the sends and receives right way around. And that really inhibits looking at the overall parallelization, which is really what you want to parallelize your algorithm. You want to be working on that one rather than playing around with little details where you've managed to get an int mixed up with a character, and that can take just so long and frustrating to find where that bug is. So I just put this example up to say everybody's kind of seen these kinds of things, and you can pull it apart and tear it apart and do different ways than I have. But it's bug prone, and it's hard to debug. And you have to be careful with memory management and such, those kinds of things that can bite you in C++. So how does Boost do it? Well, Boost is great because as templates, Boost understands objects and classes. And I think essentially I could almost stop this talk right now and just say, well, here's where Boost, in my view, is brilliant. So here we have a string, and all it's done is sends the string back and forth. But now we can use the template libraries and the C++ string capabilities. We define a string, make it hello world, and send it. That's great. The Boost library knows what a string is. And then all I have to do is define it in the receiving section there, and receive it straight into whatever the string is. And all those templates and C++ advanced libraries, the standard library, they all know what a string is. They all know how long the string is. They all handle the memory management inside it. And they generally do it better than I can if I try to program it by hand. So I lose very, very little performance doing it this way, essentially none. But of course, look at the code. I don't have to complain. I don't have to worry about it. It's a string. I send it, receive it. And indeed, everything works like that. So The rest of my examples are just good ways of doing essentially exactly the same thing. So here's a class. Just a simple class. It's got an integer, a double, and a string. If I was doing this in Classic MPI, I would have to write a serialize capability in the class where the class data is serialized, and then I can send it using classical MPI as a byte stream of some sort over to whatever the receiving processors are. And the receiving processors then have to be able to create this class, an instance of the class, and create it from that byte stream. Now, as we'll see in a second, we always have to serialize anything. We've got a class. It's got data in it. We've got to serialize it if we want to send the message to another processor. But Boost has a serialized class that handles all this. So this is a pretty trivial example. In this case, I'm just going to create a string stream and write something with a delimiter and send it off, and then one hopes that the constructor can also pull that apart and knows enough to pull it apart. So pretty straightforward for the actual class, and I'll show you in a second how we do that in Boost. And then the send receive has exactly the same problems as we just had with a string. That got to serialize it, take that string that's serialized and changed it into a character stream, send the character stream, and we have to know how long it is, all that kind of stuff, and then receive it. And receive it is just turning that backwards, receive the length, then receive the and put aside some memory for it, then receive the message itself, and then create a new class with that from that message. And again, careful with memory and all that stuff. And of course, as soon as the object gets anything like complex, this gets to be a bit of a mess. So how do we do it in Boost? Well, here is this wonderful serialization.hpp. So Boost has a serialization template library, and it's pretty clever. You can see in boldface how the Boost serialization works. You do need to give that class access to your private data in the test class, so it's a friend, great. And then there's this template. You just define a template, and the Boost library handles the rest of it. So there's a serialize, and as you can see, all I need to do is define the data that needs to be serialized. And we just pass by address there. So there was, in that particular class, there's an integer, a double, and a string. And I just use that archive template variable and stick it in. And Boost handles all the rest. It knows how to change all these to byte streams. It knows how to serialize. It knows how to get it organized. It knows how to figure out how long the whole thing is. All that. All I have to do is define what I want serialized. Now, in fact, the serialization library has a lot of capability, and you can use it completely independently of doing MPI. It's a serialization library. Yeah, you can. It's a pretty powerful library, but at least this basic level aspect is really simple. So at this point, I kind of love this. This is great. My serialize is simple, and the Boost library handles all the deserialization issues. And then, when I want to send it, well, I just send and receive. Works great. And I went one step further with this particular example. And I used, just to show you the kind of things you can start to do here, I created in the if rank equals sender, I created a vector from the standard library of these test classes. So I've got my class and I got a vector of them. And just as an example, I push back 2 of these test class. So this is a vector of length 2, so it's got 2 test class objects in it, and each one just called up the constructor for it. and then I sent the vector. That to me is just so nice. It gets rid of so many issues about how much I'm sending, whether I'm going to serialize the vector itself or each individual component of the vector. I just do it. And C++ knows how to do a vector. It knows what it's a vector of and can handle all the serialization. And it calls up that serialization route, function or member function with whatever it needs. I don't have to worry about it at all. And then the receiver is exactly the same. Create this vector and the receiver side and just receive it. That is just, again, so pretty, so easy. And of course, memory management, well, the C++ 11 templates for the container templates and such, they do all their own vector management, memory management. And you know, they are very efficient. They usually chunk it up, give you a certain block, and then if you need more than that block, they'll add a bit more to it. So they're good underneath it in trying to do the take the most optimal approach to handling memory. That's pretty, because that's another one of those places where when I actually have to do it myself, I start worrying a lot about whether I've got it the right length and when do I stop and add stuff to it, or add a few extra memory area to it, you know, where on the stack it is, or it's great stuff. And then just for fun, I put one of those C++ 11 things in the for loop. Oops, again. For an auto, the test value in the received vector, dump it out. And of course, I've given my t value an output operator. I don't know, you guys, maybe everybody's used C++ 11 or 14 by nowadays. It's standard stuff. But for me, you know, back in the original days, everything was an integer loop. And now I can kind of, it's sort of, you know, scripted language, Pythonish, right? Just some value in the vector, and C++ will handle it, all the rest of it. So I kind of like it. That auto keyword is kind of nice. It figures out what the t value is and knows all about it. Yeah, so again, so pretty, really easy to set up a serialize, and then sends and receives work great. Here's another example. How's the time here? Oh yeah, got just time to finish up a bit here. So, for instance, gather scatter operations, they're certainly supported by Boost. And in this is just a non-MPI part, the part where I take a vector. I think in this example, I'm going to chunk up the vector, send the chunks to a set of processors, and let each processor sum up their own chunk. So it's just a distributed sum going on here. So again, you can see use some of the C++ stuff, the vector double chunk, and chunk.push back that particular vector. However, in this case, I've never found any way of automatically chunking up a vector. There may be such things out there, but there it is. So that thing called chunkvec up at the top, it's a vector of those vectors, and I'm going to send each of those chunks out to each processor. So in the gather scatter, so I need a place to put. So the received vector is that's the chunk. So I'm in a processor. Each processor will receive its own chunk. And then there's a scatter, and I just need one of these. Scatter, of course, will scatter to the world in this case. It'll take that chunk vec and scatter each component, each chunk, out to all the other processes. So it does so, and it does it from the basic scatter, from the master processor, the scatter process. And then every process can sum its own vector. I think I was using an L1 norm or something in this example, so it's an absolute sum. These are mine, by the way. I don't think I used the built-in ones. And the only slight issue here is that one does, just because of changes in the syntax of the gather, you do have to have a section for the scatter process and a section for all the other processes. So the scatter process, the one that scattered it in the first place, it has to gather them all back in again. So sure, the scatter process takes all the chunk sums and dumps it into the sum, and we're off and running. And then I can sum up each of the chunk sums. Oh, sorry, takes the sum and dumps it into the chunk sums. And every other processor, they don't have to do any summing, so they just send their value back to the scatter process. So pretty standard scatter, gather, gather, scatter, and all the stuff we've just been talking about. It can use a vector. It can use my test cases if you want to scatter, gather your own objects. All works fine. All part of the deal. And another simple example of broadcast. Sure, broadcast works fine too. Right down at the bottom, I've got a broadcast, and broadcast will send in this case, a string, and it knows all about the length of the string and everything else out to out to the communicator. This particular one gets a little flashy. I just thought I'd do it. Boost MPI libraries allow you to split your set of processes into as many as you want. So you can split the world into local communicators. In this case, there's a little clever, the constant communicator ID equal world rank is less than 2. I give it an ID of COM1. If the world rank is greater than or equal to 2, give it the ID of COM2. So that means I have just cleverly set up 2 groups. Rank 0 and 1 are in my first communicator, and any process with rank 2 and above is in my second group of processors. So whatever one this processor that's running this particular instance of the code, whichever group it's in, and call that a communicator local, and it'll send that string within its local group. Right, so this is really just split that world into 2 separate things, and I can now do completely independent things within those 2 separate sets of processes. I have to say, I don't think I myself have ever used this capability in MPI seriously. Maybe others, 2 completely separate tasks that you want to run in parallel. I just ran this one just to give some output anyhow in the talk, and you can see what's happened. There's the 0 and 1 are in the first group, and the local rank 0 sent the message out to 0 and 1. And then 2 and 3 are in the next group, and again in that group, local rank 0 is still the 0th processor in that group, and it sent the message back out to 2 and 3. But when you actually look at the processor in the world, the first 2 are from the world rank 0, and the second 2 are from world rank 2. So sure enough, done what you think it is, created 2 completely separate groups, and each one does its own thing. So just kind of finishing up here a little bit, the Boost MPI, it's not complete. It doesn't have everything that Classic MPI have, but as far as I can tell, it's got everything I need anyhow. You know, non-blocking, asynchronous, the I receives, the waits, the tests are all there. You can get status, reduce works, all reduce, broadcast, and these multiple communicators and processor groups. So lots of the stuff is there. I have to say I haven't yet run any very direct timing comparisons between using Classic MPI and using MPI Boost. The literature all suggests that there's minimal performance hits. I think I mentioned before, compilers are optimized for these templates. I don't know if anybody else has had any experiences with that. I certainly haven't seen any egregious performance hits. The things seem to run pretty much the same, but it's hard to write a big code which might really take time in both languages, in both versions. So anyhow, sounds good to me. It sounds for me, certainly this advantage in actually writing the code and debugging it way overwhelms any relatively, I hope, relatively minor performance issue. And of course, as I'm sure you are all well aware, the real issues within parallelization and performance in parallel codes is in how you parallelize the algorithms, not the details of the language itself. So final slide. Yeah, of course, boost.org has got everything, so you got to go there. I really like the boostcpplibraries.com. A lot of good examples in there, pretty straightforward stuff, which give a good introduction. Anything you from all my examples from this talk are on GitHub, so go ahead. And just in the two little boxes underneath, just to finish up, of course, boost.serialization is absolutely necessary and worthwhile having a look at. The Boost itself has things like timers and date and times. I have found those to be pretty useful. They're kind of clean, maybe not timer. Some of the high-resolution timers now built into C++ are great. Maybe I just mentioned that. You know, Boost has also been a bit of a test bed for proposed new functionalities in C++. So quite a lot of the original Boost stuff was implemented by C++ 11, and more stuff went into C++ 14. So while Boost has a timer class, I think most of that capability is actually now in the language. Boost.log. Don't know about you guys, but any large file, any large code, yeah, of course you want to log everything. And the log templates are really nice. You can define severities and where output should go, and whether it should go to standard out and to a file, and what levels, all that kind of thing through templates. So I certainly didn't find it an easy template library. I think they tried to put everything in there, but it's well worthwhile. I actually wrote my own, I don't know, 20 years ago, to log both to files and emergency and very severe messages out to standard out or standard error, and so this was something that it was nice to see in Boost. And similarly for program options, you know, you can do your command line options and CL option and all those kinds of things. Boost has taken that and set it up into a way that I really liked, because I like to read options from a file, and usually in some format, so that the file, yeah, of course you want to write down essentially a two-column operation where there's a name and then the value, a name-value pair system. Well, Boost does all that. And it'll read, and it can set it up so that you can either input them from the command line or from the file and say which one supersedes the next one. So again, not the most trivial one, but I kind of liked it. So a lot of good things sitting in Boost that I really like to use. And then I put down in the lighter color the interesting. I haven't tried some of these. Boost has some ODE solvers. Don't know if anybody's ever used those, but I'd be interested. There's a Python interface, regular expressions, sorts, one microBLAS, the BLAS library, so there's a bunch of matrix vector interfaces to BLAS. And then the final one, not only does Boost have an interface to MPI, but it's also got interfaces to OpenCL, so you can do some programming, some GPU programming, for instance. I haven't tried it. Don't know if I'll get a chance to do that, but don't know if anybody else has. Anyhow, I will stop there.